Hey guys, BuildZoid here, and today we're going to be doing a PCB appreciation video for the Gigabyte Z77X-UP7 motherboard. And the UP7 right here stands for Ultra, and I should have zoomed out for that, Powerful, which is a very fitting name for a board that looks like this. So we're not going to be addressing the VRM first thing, because we'll address that later. Before we get to the VRM, we're going to cover a whole bunch of other features, and my favorite one is this chip right here. This, as you can clearly see, is a PLX chip. It's a PEX 8747, and what this is a PCIe switch. So it takes your 16 PCIe lanes from the CPU, right? You got your X16, and that will spit out 32 lanes down to the PCIe slots, so X32. Now, it doesn't actually increase your bandwidth overall. Like, you can't actually, like, let's say you put 32 lanes worth of PCIe SSDs on that PLX chip. You wouldn't actually be able to read from all of them at 32 lanes worth of bandwidth. Okay, like, it would just bottleneck on the connection to the CPU. But, what you can do, however, is put 32 lanes worth of SSDs on there and, you know, have, basically have full ATEX connections for, or full X4 connect, like, have the full, like, if you had an 8X SSD, you'd just have 8X access to it, because the PLX chip would actually be able to handle that. And if you had if you had two 16X SSDs, you could access either of them at 16x bandwidth, just not both of them at the same time. So that kind of thing. But the other and more, like, at the time, more, you know, common use of a PLX chip would be four-way SLI and crossfire support. So yeah, that's kind of the main purpose of this, is that you can run four-way SLI without having to resort to GPUs like, you know, dual-core GPUs like GTX 590s, 690s, Titan Zs, HD 7990s, 6990s, R9 295X2s. You get the idea, right? Because those cards all ultimately just integrate PLX chips into them as well, to get around the PCIe lane count limitations of a Intel mainstream CPU. But this board does it for you, so you could potentially just go buy like 4 GTX 580s, stick them in the board, and bam, you got, like, it'll still run four-way SLI, which otherwise you'd have to get an X79 board for. So, yeah, that's kind of a cool feature. Now, there's just one downside to the PLX chips. Since they are a switch and of your PCIe lanes, they add a little bit of latency to your PCIe communication, which means if you're running the, you know, if you're going X16 to just more X16, you're basically just harming your performance on the X16. So the way the board gets around that is that there's this black PCIe slot right here, and that is wired directly through to the CPU through a bunch of switches, which are probably some of these. And I'm gonna, like, well, definitely some of these, but basically the way that works is this is connected to the CPU, right? Or the PLX chip is connected to the CPU. So you can choose, if you're running a single GPU configuration, you can just stick the card in the black PCIe slot, and it's, you know, you don't have any of the latency hit of the PLX chip. And if you're running multi-GPU configurations, or you have any reason to use 32 PCIe lanes at the same time, right, multi-GPU or SSDs or capture cards or network cards or whatever the hell you want, right, it's still PCIe. You can hook up pretty much anything you want. You would use the orange slots, and you would have, like, you'd have the latency hit from the PLX chip, but you'd also have access to all of the extra lanes because you actually need them at that point. So that's really cool, that, you know, the board can actually do both. You can both have top-end single GPU performance, and you can have multi-GPU if that's how you decide to use the board. So that's a pretty neat feature right there. With the you know, CPU, direct to CPU slot right there. And then, of course, you have the quad GPU supports. So then, moving on to other features. This is a Gigabyte board, therefore it has dual BIOS. But because it's a high-end Gigabyte board, Gigabyte actually acknowledges how awful their automatic dual BIOS system is. And they give you two switches. This switch allows you to turn the dual BIOS functionality off, and this switch allows you to choose if you're on the main BIOS chip or the backup BIOS chip. And if you're wondering why on earth you would need these two switches, you've obviously never used a Gigabyte board with dual BIOS, or if you have used one of them, you've never done any real memory overclocking on one of those boards. Because what tends to happen with Gigabyte motherboards, if you're doing any kind of, you know, difficult overclocking, if the board fails to post a few times in a row, it's liable to randomly decide to switch BIOS chips. So if you're on the main one, it'll throw you on the backup one. If you're on the backup one, it'll throw you back on the main one. And that gets really, really annoying because your BIOS profiles are actually tied to the BIOS memory chip, to the actual BIOS chips. So if you save a bunch of profiles on the main BIOS chip and then get kicked to the backup one, you can't access those profiles anymore until you get back onto the main BIOS chip. And if you don't have these switches, well, the only way you're getting that to happen is if you force the board to fail to post a bunch of times, and hopefully it'll kick you onto the main BIOS chip again. But yeah, on high-end boards, Gigabyte acknowledges that that is a massive pain to deal with and gives you switches to get around that, which is great. Quite frankly, I would prefer it if they just had a main BIOS, backup BIOS switch and didn't bother with the single BIOS, dual BIOS mode whatsoever. Clear CMOS is also located right over here. Also, one workaround for the whole your profiles disappearing if you don't have these switches is to just use a USB stick to store all of your profiles, because, well, that way, like, you know, it's on the USB stick. Regardless of which BIOS you're on, you can still access the USB stick and therefore your profiles. So still, this is definitely a nice feature to have on Gigabyte boards, because Gigabyte, for some reason, just honestly, I told them that their dual BIOS implementation, I basically told them, I love that you have dual BIOS chips, because if you brick one, you still have a functional board. There's just one minor issue. The constant switching at random on failed posts is absolutely infuriating. And they said, nah, we're not changing that. It's some big thing that it's like, yeah, that's not going away. And I'm just like, you've got to be kidding me. Oh well. Anyway, high-end boards get switches, so you can turn that off. Then we got a postcode. Unfortunately, all of these things are, of course, located in the worst possible location on a motherboard that is marketed as being capable of 4-way GPU setups, right under the 4th PCIe slot. You know, it's like, if you ever wanted to see your postcode, well, it's under the GPU. Good luck with that. Also, same for the BIOS switches. Good luck reaching those. The reset switch is not quite as bad a situation, because that's actually the edge of the board, so you'd get your finger in there just fine. But I don't know about you, but I don't have an eyeball on my finger, so I wouldn't be able to, like, put my finger in there and check the postcode. Okay? So that there is just, like, this is not the only board. There's a lot of boards out there that put the postcode in my opinion, the worst possible location on the entire bloody motherboard. And yeah, this is just another one of them. This is pretty standard for boards to do, is just put the postcode where you're, like, well, admittedly, these days, most boards don't support 4-way GPU setups, but it's still a case of, like, if I have the motherboard on a test bench, I'd prefer everything to be up here rather than down there. Anyway, since I've circled up here, let's go up here. Here we have voltage read points with actual proper, like, probe hookup connectors. So, you know, instead of having to constantly hold the multimeter probes on whatever solder bumps you're trying to measure your voltage from, you can just hook the multimeter up to the board and watch the multimeter while, you know, changing settings in the operating system, or starting a benchmark, or running a benchmark, or doing whatever. You know, so this is like, I'm really annoyed that a lot of, like, high-end extreme overclocking boards these days just give you solder bumps, and it's just like, yeah, you got voltage read point, don't complain. And it's just like, but they're implemented the worst possible way. Like, honestly, if you're just going to give me freaking solder bumps, I could have just soldered the voltage measurement lines to the board myself in a lot of cases. So, still, anyway, this gives us proper voltage probe hookups. So, nice thing to have. We got a power button, LN2 mode switch, clear CMOS switch. We have a gear button, which I think is basically just like a slightly modified version of slow mode. There's also these plus and minus buttons over here. Those are for changing the BCLK and core ratio on the fly. So the cool thing about this is you could be running a benchmark, and in the middle of the benchmark, if you know, like, oh, this part of the benchmark doesn't stress the CPU as much, you can crank up the CPU ratio so you get a bunch of extra performance, and then as soon as it starts getting heavy again, you can, you know, back the CPU ratio off. So, you know, that's definitely, in my opinion, a nice feature to have on overclocking boards. It's just most of the time I would also prefer it if I could change the voltage at the same time. Right, like for some benchmarks, it would be real. Like, I know some boards technically support it, but it's just kind of a, like it's not universal. Like it's not universal. Like just like a board where you would just have buttons that you could save overclock profiles to from the BIOS. Because the thing is, there's a lot of, well, like, yeah, but basically just overclock profiles on a bunch of buttons would be really, really cool to have on a board. Anyway, so we have all of that. Did I miss anything? We have the PLX chip. We've covered that. We've covered the buttons. We've covered the postcode and how stupid it is. That's pretty much it. So let's get on to the mess. That is the this mess of phases right here, which is all of the board's different VRMs. Well, not all of them, but a lot of them, the important ones. So we have, I'm not going to try to like identify what's what in this, because quite frankly, I don't know. But I do know what is in there and how many phases everything in there has. I'm just not sure like what inductor and power stage belongs to what. So this is a 32 plus 3 plus 2 phase VRM. And that 32 phase is, of course, for Vcore. Because your quad-core i7 really needs a 32-phase VRM. And that's why I think this board is the most overkill motherboard ever made. Now, admittedly, with the Xeon W3175X, we have some motherboards out there which have VRMs, you know, on this level of insane, but those are for a 28-core Xeon, not a quad-core mainstream Intel CPU. So this is the most overkill one, even if it's not necessarily the most powerful one. It's actually definitely not the most powerful one. It's just the most overkill. So 32-phase Vcore, plus 3 for the iGPU. You know that part of Intel CPUs that until recently everybody disabled because they basically don't do anything. And then we have plus 2 for the CPU VTT, which is a memory controller voltage. More like on modern platforms, it would normally be called VCCIO. So, yeah, on this board, Gigabyte still calls it CPU VTT. Unfortunately, I don't really have a lot of experience with LGA1155, so when it comes to the memory controller voltages on this platform, actually, I have zero experience with, like, benching LGA1155. So, when it comes to the memory controller voltages here, it's like, I know they exist. I don't actually know what exactly you would want to set them to, but I do know they exist. So anyway, so we have a CPU VTT slash VCCIO. And so let's just go over how this is controlled. So the 32-phase Vcore is done by this chip right here, which obviously does not have anywhere near enough pins to have 32 phases coming right out of it. So that right there is an IR3563, which is a 8-phase controller from International Rectifier. And that goes all the way up to 2 megahertz switching frequency. Yay! And unlike on most boards, you could potentially actually set this to 2 megahertz and not have your power stages break. So, yeah, 8-phase up to 2 megahertz switching frequency. But how do you get 32 phases? Well, with these chips. And if you've been watching my videos for long enough, you should already know exactly what I'm about to write down, because these are International Rectifier 35 and 99s, and those are quadruplers and or doublers, and normally you see them used as just doublers, but this board, well, it wanted 32 phases, so it's running them in quad mode. So one PWM signal comes in, 4 PWM signals come out. The only downside to these chips is that they're dumb as bricks, because they will, like, let's say this chip right here is controlling this phase, and also this phase. So 4 of them, right? So it would literally just go, turn this, like, it would literally just interleave them in this order all the time, regardless of what the current, like how much current is going through this phase or that phase, or like, it doesn't care. It's just going to constantly, you know, turn this one on, turn this one on, turn this one on, turn this one on, and then it's going to go back to the start, and it's going to interleave them like that. So they are all out of phase, they're just not current balanced. So you do get the output ripple reduction from that. You just don't get, you know, well, you're efficient, you don't get optimal efficiency. It's not like it's a complete disaster, because obviously you do get some, like, you do get some efficiency gains. Well, not in this case, because you just have too damn many phases, but in situations where, you know, you are actually running a lot of current, that would help your efficiency a bit. But here we have 32 phases, so there's too damn many, there's just too many freaking phases relative to how much power the CPU pulls, so the efficiency is just going to suck. Because there's a minimum amount of power that is required to just turn one of the power, like, for one of these power stages to turn on and off the high side MOSFET, there's a minimum power requirement. Yeah, you know, with 32 of them, you're going to be paying that minimum power requirement times 32 as long as all 32 phases are running. And quite frankly, if they cut down this VRM to just 8 phases, it would probably, it would have better light load efficiency for sure, and it wouldn't actually necessarily have any negative impact on this board's overclocking capability whatsoever. But, you know, board's called ultra powerful. Gotta live up to the name. So 3599s are running in, you know, so that's how the board gets its 32 phases. And, you know, we have obviously one 3599 there, another one over here, and a third one over there. And then if we go to the back of the board, that's where we find the rest of the VRM, because obviously on the front you may have noticed there's a hell of a lot more inductors than there are power stages. Yes, that's because the rest of the power stages are hiding on the back of the board. It's a really good thing that this VRM is so ridiculously overkill, because normally if you put your power stages on the back of the board, well, they're really difficult to cool, because there's no space for a heatsink, and there's already power stages on the other side of the board, kind of acting as a, you know, essential, well, they produce heat. So the only way that heat from this side of the board is getting to the other side of the board is if this side of the board is hotter than the other side of the board, right? So if the power stages on the front are at 50, these can't be at a temperature lower than 50. Actually, they're probably going to be quite a bit hotter, just because, you know, in order for any heat to transfer from these to the other side, they do have to be at a higher temperature. So it's kind of like, that's why when you look at like the ridiculous Xeon W3175X, none of those boards have phases on the back of the board, because it doesn't actually work when you need to push a, you know, significant chunk of the power stage's current capability through it. Here it doesn't matter, because the power stages are barely doing anything, because there's so damn many of them. So anyway, and here's the rest of the power. Here's the rest of our quadruplers. So you have 4, 5, 6, 7, and 8. So that's all our quadruplers. And so this is, in fact, a fully interleaved 32-phase Vcore VRM. And, you know, the most ridiculous. And, you know, the overkillness gets better, because these power stages right here are IR 3550s. The predecessor of the 3555, and these are 60 amp POW IR stages. So, you know, they have all the standard POW IR stage features, like body braking mode and think integrated temperature monitoring and current monitoring and a whole bunch of stuff. It's been a while since I've checked the data sheets for these. Anyway, they include a whole bunch of functionality that you wouldn't like. To get a power stage, you literally just need a driver and a MOSFET and a high side. That's it. I mean, and your 2 MOSFETs. Like, if you have a driver and your 2 MOSFETs, you've got a power stage. But, the distinction with these, which is why they get the IR, is because they have monitoring features and control features that you don't normally have with just a driver and 2 MOSFETs. Anyway, so yeah, these are 60 amp POW IR stages, and they're ridiculously they just crank up the overkill level to 11 because there's 32 phases of 60 amp power stages for your quad core Intel mainstream CPU. And of course, how are you going to get 12 volts to your 32 phases? Through 2 8-pins, because your 3770K or 2700K, not really much of a difference in the grand scheme of things, is totally going to pull 1,000 watts or anything anywhere near that, So, yeah, this board would be much more fitting if a 3770K had like 20 cores instead of 4. Or 16. Actually, 16 cores would be a good number of cores, and that would be like 2 powers. That'd be like 2 phases per core. Though at that point, you might actually run into the issue of there's a bunch of power stages on the back of the board, and there's no effect, like there's no real way to properly cool those. So, yeah. Anyway, Vcore VRM is insanity. The Vcore VRM here is just absolute insanity. And then, the iGPU VRM and the CPU VTT just continue where the Vcore left off. Because can you see any power stages that don't look like 3550s in this blob right here? You can't, because all of them are 3550s. So the iGPU VRM on this is more capable than what you get on your average GTX. Actually, not even average. I'm pretty sure there's not a single GTX 1650 with a... Okay, now some of them have 4 phases. And those might be a bit better. But most GTX 1650s have Vcore VRMs weaker than what powers this iGPU, what will power your iGPU on this motherboard. That is assuming you didn't disable the iGPU in the first place. So, yeah, that's just more insane overkill because, discrete level GPU power delivery for an iGPU that doesn't pull anywhere near that much power or put out anywhere near that many frames. So, but hey, after the 32-phase Vcore, what can you expect? Right? You can't expect them to suddenly get reasonable about what they're going to power the iGPU with. And the CPU VTT rail is basically more of the same. 2 phases of 60 amp power stages because your memory controller is totally going to pull, 30, 40, 50 watts. Not, it's just not going to do that. But there is one kind of, the funny thing is, so this is all ridiculous overkill. But there's a voltage there's another voltage on this platform, which is the IMC voltage, as Gigabyte calls it, which it's also called by other board vendors VCCSA. And that voltage is generated by this MOSFET right here, or more like it's controlled by that MOSFET right here. And that is literally just a linear power, that MOSFET is literally just being used as a linear regulator to convert, basically there's a power plane for VCCSA over here, or IMC voltage. And going up to that MOSFET, we have, there's another power plane over here. And I assume this one, this inductor right here is VTT. I'm not 100% certain on that, but I assume it is. It kind of looks like it could be. So, you have another power plane that goes like this and around this MOSFET. So it basically grabs the VTT rail and it can lower it into the IMC voltage because that's a linear regulator. So they can't, this is one of those things we've seen, Gigabyte does this on a lot of motherboards. It's just that on a motherboard this ridiculous, it kind of doesn't make a lot of sense because essentially what this means is your IMC voltage, I'm not sure that maybe I might not be seeing something, okay? I might not be noticing some part of the VRM here, but the thing is if we look at the back of the board, there's nothing there, okay? So, essentially the downside to what they're doing here is that if your VTT is 1.2 volts, then your IMC voltage is absolutely limited to 1.2 volts. Now, the great thing is, if I remember, I'm not sure how similar Sandy Bridge is to Sandy Bridge E. But at least on Sandy Bridge E, you would never actually want to really, like, my experience with Sandy Bridge E is that this voltage is supposed to be at 0.95 volts and never any higher or any lower, because doing anything to it that isn't 0.95 volts makes things less stable. And that's been my experience with, like, my 3960X. So, unfortunately, I never worked with, like, a 2500K or a 3770K or a 3570K, but now that I have this board, I am definitely looking into acquiring one of these because I want to run this thing, okay? It's great that I have it and I can look at it and go like, ooh, phases. So many damn phases. Yeah. But, you know, I'd honestly actually want to do more than just admire the thing. I'd like to actually run it because it's kind of sad when you have this much motherboard and, you know, it doesn't even get to power, like, it doesn't get to even be powered on and abused with overclocking. And then for the you know, VTT rail, if I remember correctly from, well, for Sandy Bridge E, I think it was normal to run that at like 1.05 to 1.15. So I can totally I can see that if, you know, if Sandy Bridge and Ivy Bridge behave exactly like Sandy Bridge E and Ivy Bridge E, where you don't actually want to raise this voltage ever, at all, then yeah, I can totally understand why Gigabyte decided to go just with a MOSFET, because quite frankly, this is going to be locked at 1.95 volts, and you're never going to run into the issue of, oh, you're not going to want to set your VCC, like your IMC voltage above your VTT voltage ever anyway. And so it's not an issue that it's forced to always be lower, because the only thing that MOSFET can do is lower the voltage. It can't raise it. Still, it's just kind of like, you know, we have all these phases, and you couldn't have spared one for the you know, IMC rail. Like, really? They could have honestly just gone with, like, instead of running 8 there, they could have gone for like 7 plus 1. That would have been a 28, and you would have had a plus 1 on here for IMC rail. But I guess they really wanted 32 phases. Because this motherboard is still from that era of motherboards where there was essentially kind of a phase count war going on between some of the board vendors. Asus weren't really part of it. Like, Asus has been running basically 4-phase with doubling or true 8-phase on their motherboards for freaking ages. So yeah, they weren't really, at least for the ROG boards. For their mainstream boards, I think they were just as involved in the, hey, we got more phases than you do situation than all the other board vendors were in. But Gigabyte was definitely winning. Okay, I can tell you that Gigabyte was winning, because you literally can't go above 32. And you can't use power stages more, like, at the time you couldn't really get power stages better than 60 amps. So this board was winning in the phase count war. It may not have been winning at a lot of other things, but when it came to phase count, it was winning. And obviously 28 plus 3 plus 2, I mean, plus 3 plus 2 plus 1 is less than 32 plus 3 plus 2, right? More phases, more better. Even if it means that one of your voltages is literally restricted to always be below the other one. Anyway, so that's what we have going on over there with the IMC voltage. And then for VCC PLL, so I'm not 100% certain on how this works, because like this MOSFET is again being used as a linear regulator for VCC PLL. The issue is I don't actually know what voltage it's regulating down. So it could just be if it was low current, if that rail is low current enough, you could totally run it off of just straight 3.3 volts. But they also put it suspiciously close next to this linear regulator right here. And that one, you can see a power plane going to the PLX chip over there. And that is probably 1.8 volts for the PLX chip, which just so happens to be the same volt, like 1.8 volts stock is what you would, VCC PLL at stock is 1.8 volts. So I don't think it's necessary, because again, if this rail is low enough current, then yeah, you can just, well, at the same time, they could have just gone for a proper low dropout regulator instead of using a freaking MOSFET there. So yeah, I'm not sure. I'm probably, like, I'll have to power the board on and check what's going on with that, because if they're overvolt, like, because the thing is, if you wanted to raise your VCC PLL to say 2 volts, you would basically have to overvolt the PLX chip to do that. assuming that this MOSFET is literally just regulating whatever this outputs down into VCC PLL. Unless the old PLX, unless the PEX 8747 that this board uses runs on 2.5 volts, which I doubt, because as far as I know, that the PEX 8747 has a 0.9 volts, right? Like something around 0.95 volts and a 1.8 volts rail. Unfortunately, it's actually impossible to get a full detailed data sheet for one of those chips. Yeah, this is kind of question mark to me. Oh, and I forgot to address how the iGPU and the CPU VTT rails are actually controlled. So that 3+2 portion of the VRM, that there, is produced by this chip over here. And, I mean, that just doesn't seem like an ideal way to do things, does it? Because you're running control lines. Well, I'm not sure. They might be running them around or something. But the shortest path is definitely to just go like that, because the iGPU VRM is in this area, and the VTT is down here, and the controller for both of them is over here. And I actually checked that because the current sensing circuitry over here, it measures 0 ohms to that, and it measures 0 ohms to a inductor up in this area as well. So that tells us that, yeah, this runs IGP, like this runs the iGPU. It also runs the VTT. So that's great. Yeah, so that there is an IR3570. It goes up to 3+2 phases, up to 2 megahertz switching frequency. And I mean, like, you know, plenty of overkill for what it has to do. It's just kind of odd that, well, it's not... Like, if you look at it from the perspective of where could they possibly put that chip, then it makes perfect sense that it's right here. But in a sort of like, how do you hook that up to what it's actually controlling sort of perspective, it's kind of a bit of a, like, well, I mean, I would assume you'd prefer to not run random PWM lines and current sensing lines through where the memory traces go. You know, that would just be my guess, that might not be ideal. Admittedly, if this board has enough layers, and this being a high-end board could, you know, it could have 8 or 10 PCB layers easily. You know, it might not be an issue to run a line through the area, but still, it's just kind of a odd. Like, it's a bit weird, because normally the goal is to get your voltage controller as close to the thing it's controlling as possible. And, well, I mean, there is no space anywhere, but yeah, it honestly kind of seems like this board is in some ways potentially compromised just for the sake of getting 32 phases, which is kind of a shame in my opinion. Anyway, I just ruined my color there. So anyway, that's what's controlling the VTT and iGPU rails. Let's move on to the memory power, which is more overkill. And this one doesn't have a controller located a mile away. So that's another IR3570. I mean, yeah, 3570, 3570. It just sounds weird when you say 3570. Anyway, that's another 3-phase. 1, 2, 3. And it's yet more IR3550 power stages. Because, you know, your memory sticks are totally going to burn 50 or 100 watts of power, you know, something in between those two. Totally going to happen. So yeah, that's just more ridiculous overkill in character with the rest of the board. Right there. That pretty much covers the voltage regulators. So at this point, something that's kind of interesting about this board is the actual capacitors that Gigabyte opted to use on these. Those are actually Panasonic. And the reason why I'm pointing that out is that if you look at modern motherboards, basically everybody runs for the high end. It's all Nichicons. So everybody uses like Nichicon FP series capacitors, and they come in like 5K or 10K or 12K or whatever random 1,000-hour rating. Like ASRock has the highest one. It was kind of it's a kind of a similar situation to the phase race. Except with the capacitors, it kind of has a bit more merit to it because, well, the board should, like, they'll last longer, right? Now, will it be practical for the average user that they have a capacitor that can survive 12,000 hours at 105 degrees? Well, if they do like, depending on how they run the board, potentially, but most people probably don't run their boards at, 105 degrees, 105 degrees, like they don't run them stressed to the point where the capacitor banks are hitting 105 degrees for extended periods of time. Anyway, this board is just kind of unique in that it uses Panasonic, which I'm not sure if Gigabyte used Panasonic everywhere at the time. But definitely these days, like high-end board, you're going to be looking at Nichicons, unless you're looking at an MSI board, which I think they use Nippon Chemicon. So MSI is kind of an exception. Everybody else that that I've been paying attention to is on Nichicons. So that's just a random little detail about the board. Now, the other thing I wanted to show about this board, which this is something that I wanted to show in a video for a while, but I didn't really have, like, I couldn't figure out a good excuse to show it, like, because in and of itself, it's such a short little thing. You see that? You see that there? You see this? You see that? And this, and that, and this, and that. You may be looking at, you might be like, Buildzoid, why are you drawing all these T's? Well, that's because this board has T topology for its memory layout, which I just think is kind of neat that you can actually see it on this layer of the board. Now, obviously, the rest of this is buried several layers deep, and some of it's on the other side of the board, so, we can't see it over the DIMM slots. But yeah, this is a T topology board, which is maybe part of the reason why, like, as I understand it, this board doesn't exactly have a reputation for being the best memory overclocker. This probably has something to do with that, because the thing about T topology is it's optimized for it's optimized for having all of the DIMM slots fully populated, because what this right here does is most of the time you end up with potentially a little bit more trace length, but the bigger issue is this right here. If there's no DIMM on the end of that, that is an unterminated just bit of wire hanging off the signal line, and this causes a bunch basically it causes ringing issues and just a bunch of interference. And if you have two DIMM slots on a T topology, if you run one DIMM per channel on a T topology board, it tends to not clock that great because of the way this is laid out. Now, if you had a daisy chain board, instead of having this lovely thing right here, you'd basically just go like that, right? Like this whole thing would just be one straight line like that. So you'd have a little bit less length, but much more important. But the downside to going with a daisy chain is that the DIMM on this pin, right, the DIMM connected to this pin actually has a completely different timing to the DIMM at the end of that. So daisy chain biases towards two DIMM configurations, whereas T topology biases towards one DIMM per channel configurations for daisy chain, two DIMMs per channel for T topology. So, ideally, if you were running this board, which it makes sense because this is like a super high-end motherboard, so Gigabyte was probably designing this memory layout with the idea of like 4x8 configurations, 4x4, or even 4x2, right? Like any of these 4x something configurations, that's probably what this board was designed for, because it's a high-end motherboard. A lot of people would want to run 16 gigs or even 32 gigs of DDR3. And so it didn't really make sense to make a board where if you go to 32 gigs of DDR3, it actually clocks worse than if you were on 16, right? But the reverse is true. But the end result is that the reverse happens with this board, where it should potentially clock worse on 2x8 than on 4x8. Which, kind of a like that. That's a compromise. That's basically a decision board vendors have to make when designing their boards. And for a high-end board, that like. The thing is this also tries to be like an extreme overclocking board, and this isn't this isn't necessarily ideal for the standard of like 2x2 gig memory configurations that are really popular for DDR3 benchmarking. Now, what like, since this board is T-topology, I do actually want to test out running like 4x2 configurations of DDR3 once I get a CPU for it, and comparing it to like 2x2 as well. Because maybe 2x2 actually works just fine because the memory controller can't deal with 4x2 anyway. And then the layout of the board is less of an issue than the fact that the memory controller just can't deal with it. So anyway, so this is a T-topology board, and, you know, you can clearly see the T's that T-topology gets its name from just all over the back of this board. So that's pretty neat. And finally, the heatsink. Yeah, boards used to have fins, and then Haswell happened, and then the heatsinks stopped having fins, and now they became fashion accessories. And now, you know, these days we're back to having fins, or at least more fins, but I don't think we're anywhere near anything like this yet. Yeah, this board had a hell of a lot of fins. Now, ultimately, since the VRM is a 32-phase, it really doesn't need this. But this right here is actually pretty useful because the PLX chip, those tend to get pretty hot. So this right here is a dedicated heatsink for the PLX chip, and ultimately that's probably going to be dumping heat straight into the chipset. Which is fine because there's yet more surface area. Like, your chipset doesn't put out that much heat, but if it did put out a lot of heat, well, this board would handle it with ease. So, yeah, quite the heatsink assembly. And they also have this sort of heat spreader for the back of the board. And this is a heat spreader because you can't call it a thermal buffer, I guess, heat spreader, but not really a heatsink because it's essentially just a metal slab. Like, it's a slab of metal with some thermal pad on it. It doesn't really change the surface area of the VRM that much, if at all. So, yeah, but they do have this to try spread the heat out into the board a bit. And also just get some more mass on the back of the board. I guess it also kind of acts as protection for the power stages, which is kind of a secondary effect of it. But yeah, that's the heatsink assembly. So, and the heatsink assembly is just as overkill as the Vcore VRM, right? So, yeah, and that is the Z77 UP7 from Z77X-UP7 from Gigabyte, the most overkill motherboard ever built. Mostly because they put a 32-phase VRM on a motherboard that supports quad-core CPUs at most. So, yeah, but still, it's a really cool board, and there's some stuff on this board where it's like, well, I can understand why we don't see PLX chips very often, because again, they're really expensive these days. Back when this board was built, this was like $50. Now it's $100. But you know, it's still like things like the VRM heatsink, for example, like, it really shouldn't have gone away. I don't like the 32 phase is not actually practical. I don't see, like, there's no loss in not having like, boards not having 32 phases for their Vcore. That's not a loss. Okay, that's fine. That's perfectly fine. If anything, it's probably for the better. But yeah, you know, this is just a board that I really wanted to take a look at because partially it's orange, and also because all them phases. So yeah, I've run out of things to say, so I guess thanks for watching. Like, share, subscribe. Like, share, subscribe. I'm really tired right now, so I've like, share, subscribe. Leave a comment, leave any comments, questions, suggestions down in the comment section below. And if you'd like to support what I do here with actually hardcore overclocking, I have a Patreon and Teespring. And so on Teespring, you can get things like shirts, stickers, posters, socks, you know, and those all, you know, support the channel. And then there's, of course, the Patreon if you don't want to buy anything in order to support the channel. And I forgot to mention, well, I forgot to thank the very generous fan of the channel who sent this beast of a motherboard in. Yeah, now I really want to get a CPU for it, which shouldn't be a problem. Like, at this point, the quad-core i5s are, like, super cheap, so it's just a matter of time. I'm just busy with, like, we all know that my GPU collection is far too big, and I want to burn through my GPU collection and then start working on my backlog of DDR3 motherboards. Yeah, so the thing is the UP7 is actually kind of hard to find these days. Anyway, I'll shut up now. This video is getting far too long. Where's the mouse? There's the mouse. Where's the stop button? There it is.